and welcome to another Common Core Geometry lesson by eMATHinstruction. My name is Kirk Weiler, and today we'll be doing Unit 4, Lesson number 7, on inscribing regular polygons. So this is the last lesson of Unit 4, which has been devoted to various types of constructions and the mathematics behind those constructions. Today we're going to be looking at how to put various polygons, and we'll talk about which ones, inside of a circle so that the vertices of the polygons just touch the circle. And let's kind of get into that now. All right, so there are three important regular polygons that we can inscribe in a circle, okay? One of those is simply, the square, all right? And we'll see the mathematics and the technique behind inscribing a square. Remember, as with all constructions, you want to make sure that you have a straight edge available today, and you want to make sure that you have a compass, and that's all we'll really need, the straight edge and a compass. Now, besides the square that we're going to inscribe in a circle, we'll also inscribe an equilateral triangle, and we'll inscribe a regular hexagon. And remember, the idea behind regular polygons is that they are polygons whose sides are all the same length, and whose angles all have the same measure, okay? So the square, the equilateral triangle, and then the regular hexagon, the regular six-sided figure. And that's going to be it. Those are the only ones we're going to be doing. The constructions themselves are actually quite easy. So we'll spend a little bit of time today doing the construction, and we'll also spend some time today justifying why the construction works, as we always do. So let's get into it, and let's start with the square, inscribing a square in a circle. Okay. Now remember, whenever you're given a circle, you'll always be given its center point, and that's actually quite important. If we were just given a circle and we had no center of the circle, that would make this a nearly impossible construction to do. Okay, but let's jump right into it. Let's see how to do this construction. Exercise number 1. A circle with center point O is shown below. Do the following. Letter A, construct, i.e. draw, a diameter of the circle in any direction. Mark its endpoints A and B. All right, so I've got to draw a diameter, and of course a diameter is any line segment that goes all the way across the circle and passes through its center. So I'm going to take my straight edge and I'll bring it up here. And again, it can be in any direction you want. I'm going to be drawing it horizontally, but it can be in any direction you want. Now, it says to mark the endpoints A and B, so why don't we do that? Let's mark this as endpoint A. And this is endpoint B. All right, simple enough. So, the next part of the problem, letter B. Construct the perpendicular bisector of AB. Mark its endpoints C and D. All right, now the perpendicular bisector is one of those constructions that we've actually done in previous units, and we've done it time and time again in this unit. So what I'd like you to do is pause the video now and see if you can remember how to create the perpendicular bisector of segment AB. Don't worry about the circle. Just treat segment AB as if it's just sitting there by itself and draw the perpendicular bisector to it. Take a few minutes. All right, let's go through it. So remember how to do the perpendicular bisector. What I'm going to do is I'm going to put the center of my compass at point A or point B, it doesn't matter which one you start with, and I'm going to expand the radius of the compass so that it is more than half the length of segment AB. That's pretty easy because, of course, O serves as the midpoint of segment AB. Now what I'm going to do is I'm going to draw an arc up here, and I'm going to actually draw that arc. Whoops, I'm going to try to get the center back a little bit better at A. I'm going to actually draw that arc all the way down here. Okay? Now, without changing the radius of my compass, remember, I'm now going to put the sharp end at B so that I have the center of my arc again. And I'm going to draw the arc once again. Now, just as a slight review, remember the point here is that this intersection point up here and this intersection point down here are equidistant from A and B. Okay, which means that both of those lie on the perpendicular bisector of segment A and B, so all we need to now do is connect them with a line segment. So let's bring our straight edge up, rotate it, and draw that perpendicular bisector. All right, now, a little bit of a mistake maybe in the directions here. It says mark its endpoints C and D. What I really want to do is I want to mark the points where it intersects the circle as C and D. The perpendicular bisector itself you could claim is a line, so it has no endpoints. But I want to mark where it intersects the circle at C and D. Okay? Now, letter C says, draw a polygon ACBD. In other words, I want to connect A to C, C to B, B to D, and D to A, and I claim that will be a square. All right? And no, not the kind of cool type of square like me, but just your garden variety square. So let me bring this up. Whoop. Get it a little bit better there. For me, it's easiest to then just rotate it down and connect point D to point A. Bring it over to B. Whoop. And rotate it down. And now I claim that ACBD is a square. Now I know that you're used to seeing squares in this kind of orientation. But remember, a figure doesn't depend on how it's oriented in space, it depends on its properties. And the properties of a square are that all four of those sides are going to be equal in length, and then all four of these angles will be right angles. But that's really it. So pause for a minute, not the video, but just pause for a minute and think about this. To create a square, what we had to first do was actually draw the diagonals of the square. All right? One of the diagonals is that diameter, and the other diagonal is this diameter. And the key is those two diameters had to be perpendicular to each other. Right? All four of these are right angles. Okay? But it's actually a fairly easy construction. What I'd like to do in the next exercise is look at why that construction works. Why do we get a square? So let's go ahead and do that next. All right. Now what I've done is I've actually reproduced the construction that we did just down here, and I even made it so that the diameter is a little bit more slanted, the first one, but then that's the second one, and we've got the arcs here and there and all of that. So let's take a look at what this problem in exercise number 2 asks us to do. Let's now understand the logic behind why ACBD in the last exercise must be a square, why it must be a square. We will do this by examining 4 triangles created by in this diagram. Right? So in other words, this triangle, this triangle, this triangle, and that triangle. Those 4 triangles are the key to understanding why this must be a square. So letter A says, what triangle congruence theorem could be used to prove that triangle AOC is congruent to triangle BOC, which is congruent to triangle AOD, which is congruent to triangle BOD? Explain your choice. Because these triangles are congruent, what can you conclude about the sides AC, BC, BD, and AD? Explain. All right, so there's a lot in this question. The first question is, which of the 5 triangle congruence theorems, side, 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 angle, hypotenuse, leg, and angle, angle, side, which of those 5 could be used to justify that those 4 triangles are congruent? All right, take a moment with that, pause the video, and think about it. All right, let's talk about that first. Well, one thing that we know is that BC, right, DC, my mistake, is the perpendicular bisector of AB, which tells me, as I've already marked up on the picture, that these 2 segments are congruent. But at the same time, right, DC is a diameter because it goes through the center of the circle. And because it's a diameter, it means that OC and OD are also radii, which means they must also have the same length. So this side is congruent to that side, which is congruent to that side, which is congruent to that side. Furthermore, right, we know that CD is perpendicular to AB, which makes that a right angle, that a right angle, that a right angle, and that a right angle. So I have a side congruent to a side, congruent to a side, congruent to a side, and an angle in between each of those congruent sides. We can say all of these are congruent by the side angle side theorem, right? The side angle side theorem. All right, now, what does that then tell us that we can conclude about AC, BC, BD, and AD? What can I say about all these hypotenuses of these right triangles? I can say that AC is congruent to BC, is congruent to BD, is congruent to, and there goes my red again, AD by CPCTC, right? Those are corresponding parts of those congruent triangles. That's congruent to that, which is congruent to this, which is congruent to that. All right? Now that's kind of cool, right? Really, remember, the overall purpose of this problem is to justify why this figure must be a square. And there are two things that make a figure a square. Number one, all four sides are the same length. Check. Right? All four sides are the same length here because those four right triangles are congruent, and therefore their hypotenuses must be congruent. But let's take a look at letter B, because the other piece of the puzzle with the square is to ensure that all of these angles must be right angles, right? All of these must be right angles. So that's going to be part B. Let's take a look at it. Since triangle AOC and BOC and BOD and AOD are all isosceles right triangles, okay? In fact, let me kind of redraw triangle AOC down here in an orientation that we can kind of look at a bit more. That's this guy right up here, right? I'll kind of mark all these things down that we had on the diagram. What must be the measure of each of its acute angles? So what is the measure? What are the measure of those two angles? I'd like you to take a minute and figure this out, because you certainly have the tools to do so. All right, well, let's talk about what these things are. Each one of those things will be a 45-degree angle, and that's good to know just off the top anyway. But think about why this is, right? In an isosceles triangle, the two angles that are opposite of the congruent sides must be equal. All right? They've got to be equal, okay? And since the three angles of a right triangle must add up to 180, right? Once we take that 180 and we subtract off the 90, we'll be left with 90 degrees that must be split evenly between those two acute angles. And so each one of those must be 45 degrees. But now think about this for a moment, okay? And now I'll actually purposely change to red. That means this angle is 45 degrees, this angle is 45 degrees, this angle is 45 degrees, etc. Let me just get them all in there. Whoops, where did my 5 go? I guess it never showed up to begin with. All of those angles are 45 degrees. But now, right, since the whole is the sum of its parts, then that angle, as well as this one and this one and this one, must be 45 plus 45 and has to be 90 degrees. All right. And that finishes off why this has to be a square, right? We know because the triangles are all congruent that the four sides must be equal lengths, and then because they're isosceles right triangles, they just have acute angles that are 45 degrees each, and when we sum those together, we get that 90-degree angle. All right? And that's what makes a square. Now, for the rest of the lesson, we're going to be concentrating on inscribing equilateral triangles and regular hexagons in a circle. Those are also fairly easy constructions to do. The math behind why they work is a little bit more challenging, and we're going to actually dive in to the math first before we do the construction, okay? So let's take a look at the next exercise. All right, exercise number 3. In the diagram to the right, A, B, C, D, E, F is a regular hexagon, okay? So this outer figure is a regular hexagon, okay? Which means all of its sides are the same length and all of its angles have the same measure. So let's take a look at what letter A asks us to do. What triangle congruence theorem could be used to prove that triangle ABC is congruent to triangle CDE is congruent to triangle EFA? Okay, now remember, it's important for you to understand when you look at this kind of statement which 3 triangles we're talking about, because there's kind of 4 triangles sitting here in the picture, okay? But we're talking about that triangle, that one, and that one, not the one in the middle, although it's the one in the middle that we kind of care about. Okay, but first, take a moment, pause the video, and think about which of the 5 congruence theorems you'd use to prove that those 3 triangles are congruent to each other. All right, let's talk about it. Well, because it's a regular hexagon, what we know is that this side is congruent to this side, is congruent to this side, this side, this side, and this side. All those sides are the same length. We also know, because it's a regular hexagon, that this is congruent to this is congruent to this. We also know that this angle is congruent and this, etc. But I don't really care about that angle and that angle and that angle, so in fact, I'm going to just erase that not to muddy up the picture. But now it should be fairly obvious, and it's exactly the same one that we used in the last problem. These 3 triangles are congruent by side, angle, side, right? We've got sides, congruent to sides, and then we've got the included angle between them that's also congruent. So it's side, angle, side. I would dare say side, angle, side might be the most important of the 5 congruence theorems, but of course that's debatable. Now, all right, letter B. Since these triangles must be congruent, why can we now conclude that triangle ACE is equilateral? Why can we do that? Think about it for a moment. All right, well, it's simple enough, right? Because these 3 triangles are congruent, this side must be congruent to this side, must be congruent to this side. Let's actually write that down. So AE must be congruent to AC, which must be congruent to EC, okay, by CPCTC, right? Those are the corresponding parts of those 3 triangles. They're across from the congruent angles, so they have to all be congruent because corresponding parts of congruent triangles are congruent. But then it's equilateral. Well, maybe even use it. So then triangle, get rid of that. Triangle ACE is equilateral because it has 3 congruent sides. Or you could just say by the definition of a equilateral triangle, right? Now, by the way, notice something that's a little bit strange. In the last exercise, we looked at the fact that the 4 sides of that square were congruent using, well, same idea, the CPCTC reasoning. But then we had to go on and we had to prove that all of its angles were 90-degree angles. With triangles, that's not the case. An equilateral triangle certainly has all 3 angles congruent to one another and all equal in measure to 60 degrees, right? 180 divided by 3. But we don't actually have to prove that the angles are all 60 degrees because in a triangle, once all 3 sides are congruent, all 3 angles are congruent. The same is most certainly not true in what's called a quadrilateral, a 4-sided figure. You can easily have 4 sides that are all the same length, but absolutely no 90-degree angles. And we'll look at that a little bit more when we get into the unit on quadrilaterals. But now, let's do the constructions. Because strangely enough, the construction of the equilateral triangle is going to be based on the construction of the regular hexagon. So let's get into it. All right, let's inscribe a regular hexagon and an equilateral triangle all at once. And it's an easy construction again. Let's take a look. Exercise 4. Given the circle below with center O, do the following. Draw a diameter in any direction. Okay, so just like with the square, we start with a diameter. Okay, and my ruler's all set up, so I'm going to just start by drawing this diameter in. Actually, I think I'm going to make my line width a little bit thicker so you can see it a little bit better. There we go. Maybe move my ruler out for a second. From each of the endpoints of the diameter, draw an arc whose radius is the same as the radius of the circle. Each arc should intersect the circle twice. Mark the intersection points of these arcs with the circle. From each of the endpoints of the diameter. Okay? So this is where my center is going to be. All right, so let's do that. Let's take my compass, put its center at one of those two ends, stretch out the actual radius so it's the same as the radius of this circle, and draw an arc. Okay? Now what I really care about is I care about where that arc is intersecting the circle. Okay. It says mark the intersection points of these arcs with the circle. So here we go. I didn't mark the endpoints of the diameter, so I'm going to do that right away. Okay. And notice, if I mark the intersections of the arcs and the endpoints of the diameter, I have 6 total points. Exactly what I need for that hexagon. Letter C says connect these intersection points and the endpoints of the diameter. Label the figure A, B, C, D, E, F. This will be a regular hexagon. Okay, let's do it. And I think it's going to be easiest for me now. Let's see if I can remember how to do this. Nope, not that. This, nope, this, nope. Okay, give it up. We'll just go with the ruler now. I was going to try to use my line tool, but I can't currently find it, so let's just draw them in the old-fashioned way. Bring this down here. Why don't you go ahead and connect them as I am. You'll likely be able to do it a little bit faster than me, or significantly faster. Wasn't too bad. Getting a little bit better with the line tool. There we go. Mark it A, B, C, D, E, F. And there is your regular hexagon. It's not so bad, huh? We draw a diameter in. From the 2 endpoints of the diameter, we draw 2 arcs, right? Those arcs have a radius that's exactly the same as the radius of the circle that we're trying to inscribe the regular hexagon in. And there we have it, right? A, B, C, D, E, F. Now letter D says, using what we learned in number 3, the last problem, construct an equilateral triangle. State the name of your equilateral triangle below. All right, so just in case you've forgotten what was on the last slide, let's go back there just for a second, okay? Now notice, what did we really see here? We saw that if we connected every other vertice of a regular hexagon with line segments, we would get an equilateral triangle. And it wouldn't matter which ones we started with. We could start with B and connect it to D and connect it to F, or A, C, and E. There's only 2 that you can really get out of this. But you just have to make a choice. So let me go over to red. That way it'll have a nice little contrast. But now, let's kind of keep it. I'll keep it in the same orientation I did before. I think we'll connect A to C and connect A to E. And then we'll connect C to E. Now, depending on which 3 you connected, equilateral triangle, right? Depending on which three you connected, you could have a different name. But for us, we've got triangle, what was it? ACE. All right. Now, why this construction works, specifically why we get a regular hexagon when we do that business with drawing those two arcs and then finding their intersection points, you're going to be exploring on the homework. In fact, you'll kind of go through the same thing that we did before in terms of why did the side lengths have to all be the same, why did the angles all have to be the same, etc., etc. But we'll let you play around with that one on the homework. Let's wrap up the lesson. All right. So we saw the last of the constructions that we'll see for some time. We'll come back and we'll do some more of them in a later unit when we have a little bit more math in our tool bag. But we saw the last of the constructions of Unit 4 in today's lesson. Specifically what we looked at was how to inscribe a square, a regular hexagon, and an equilateral triangle inside of a circle so that the vertices of these regular polygons lie on the circle itself. All right? These are three constructions that are specifically pointed to in the Common Core geometry standards. So if you have to take a standardized exam at the end of the year that's kind of benchmarked to those standards, these are three that you have to know. And they're not all that difficult. The homework should provide you with plenty of practice to sort of reinforce them in your head. But certainly if you have an exam coming soon, you'll want to kind of review these and really understand how to do them because they're fairly simple and you'd hate to lose credit on something that's simple. All right, for now I want to thank you for joining me for another Common Core geometry lesson by eMATHinstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.